Welcome to my channel. Today we are going to discuss some important problems from the circuit analysis paper for the preparation of the competitive exams. The first question you see, when two two-port networks are connected in parallel, it is convenient to use dash which parameter? Open circuit impedance parameter, short circuit impedance parameter, Z parameter and Y parameter. So already we discussed this problem in one TRB question. If the two two-port networks are connected in parallel means in order to find out the overall parameter of that particular network, the Y parameter is very convenient. Okay, so Y parameter means it is a admittance parameter. Okay, so similar to this, if two two-port networks are connected in series means in that case, in order to analyze that network, so it is easy to use the Z parameter. Okay, so this is a very important and repeated question. Then the next question you see, in RLC series circuit, the impedance at resonance, okay, impedance at resonance is dash. Okay, so in series resonance and parallel resonance circuits, so already we discussed in circuit analysis. So if you want to learn more about that one, so already I posted all lecture videos related to this subject circuit analysis in a separate playlist in the name of circuit analysis and circuit theory. Okay, so if you want to learn that one, I will give link for that playlist in the description box. You can refer it. So the in series RLC circuit, impedance at resonance condition is R. Okay, so already in resonance condition, the reactance of inductance is cancelled by the reactance of capacitor. So at a resonance condition, that RLC circuit, it behaves as a purely resistive in nature. Okay, so that's why the impedance at resonance condition is capital R. Then you see the next question. In figure 1, RA, RB, RC values are 20 ohm, 10 ohm and 10 ohm respectively. The resistances R1, R2, R3 of an equivalent star connection are dash. Okay, so here you see this is the diagram given. This is the delta network. In delta network, the resistor value RA, RB, RC is given as 20 ohms, 10 ohms and 10 ohms. So we have to find the corresponding star network values. Okay, so already there is a conversion of we can convert the delta network into star and star into delta. Already you know the formula. So if you are converting this delta network into star network means, so what is the corresponding resistance value? R1, R2, R3 we have to find out. Okay, so you see that this is the value in delta network means, so first you check if the given all values in delta network is equal or not. Okay, if it is equal, so it is very easy to convert into star. Okay, so already you know the formula. The star value is equal to the delta value divided by 3 if all these three resistances are equal. Okay, but here this RA value is different, RB RC value is same, so that's why we have to use that formula. So if you want to convert this delta into star means, so the value R1. Okay, so you see this resistance R1 is connected in node A with respect to this neutral node. So that R1 is calculated by, so here you see in delta network, you see this node A. So in this node A, what are the two resistances connected in node A? This RB and RA. Okay, so you just multiply these two resistances divided by the addition of all three resistance. This is nothing but R1. So R1 equal to 20 into 10 divided by addition of this three resistance 20 plus 10 plus 10. So the answer is 5 ohms. Okay, similarly, if you want to find the resistance connected in node B. Okay, so here we are considering it as a R2. So this R2 is calculated by, so you see in node B, what are the two resistances connected in node B? 10 and 10. So you just multiply the 10 and 10 divided by addition of all three resistance, it is a 40. So the answer is 2.5 ohms. Okay, similarly R3. This R3 is calculated by, similarly R3 is connected in node 3. Okay, so in node 3, what are the two resistances connected? 20 and 10. So you multiply 20 and 10 divided by 40. So the answer is 5 ohm. So the resistance R1 is 5 ohm, R2 is 2.5, R3 is 5 ohm. Okay. So this is the delta to star conversion problem. Then the next question, what should be the value of resistor R if it has to observe maximum power from the source? Okay. So this is the maximum power transfer theorem. So this is the circuit given. So in this circuit, if the maximum power is delivered to this load resistance R means, so what should be the value of R? That is the question. Okay. So already you know, according to the maximum power transfer theorem, whenever the value of this R is equal to RTH. Okay, RTH means the Thevenin's resistance across this open circuited terminal of this throughout the network. So whenever this load resistance R is equal to RTH, at that condition only the maximum power derived from the circuit will be delivered to the particular resistance. Okay, so we have to find out the RTH, then that RTH value is equal to the R. Okay, so here the question is we have to find out the R value. Okay, so you see the thing. So in order to find out the RTH, already know the procedure. In order to find out the Thevenin's resistance, first we have to remove this load. Okay, this R is the load, you just remove it. And in order to find out this RTH, in the remaining network, we have to make all voltage sources and current sources are zero. Okay, so here you see there is one voltage source is there. This voltage source, we have to make it as a short circuit. Okay, since if voltage source value is zero means we have to make the short circuit. So what about the remaining diagram? So the remaining diagram 8 ohm and 4 ohm connected in parallel. So you see this is the equivalent circuit after short circuiting the voltage source and open circuiting the load. Okay, so now you see we have to measure the equivalent resistance across this open circuited terminal. Okay, that is nothing but R equivalent or RTH. Okay, so here 8 ohm and 4 ohm connected in parallel. So the parallel combination of 8 ohm and 4 ohm, you just calculate. So 8 into 4 divided by 8 plus 4. So the answer is 8 divided by 3 ohms. Okay, so here you see the option is given 3 by 8, 8 by 3, 4 and 8. So this 8 by 3 ohms is the correct answer. So whenever the resistance value, okay, so in this circuit, this resistance R is equal to 8 by 3 ohms. At the time only, the maximum power derived from this source will be delivered. Okay, this is nothing but a maximum power transfer theorem. Then the next question, the Norton's equivalent circuit shown in figure 2 is drawn from figure 1. Okay, the value of ISC and R equivalent in the figure 2 is dash. Okay, so this is our given circuit. This is our figure 1 given circuit. So this second figure is the Norton's equivalent model for this given circuit. Okay, this is the Norton's equivalent model. Already you know Norton's equivalent means any complex circuit with any number of resistances, voltage source, current sources can be replaced by simply one current source in parallel combination with the total resistance. This is nothing but a Norton's equivalent. So if this is the Norton's equivalent diagram for this our given circuit means we have to find out this ISC value and R equivalent. So we have to follow the Norton's procedure. Okay. So first one, so in this we have to find out ISC, short circuit current as well as the total resistance. Okay. So one by one we are going to calculate. So first one, we have to find ISC. What is mean by ISC? Short circuited current. Okay. So here we have to draw the equivalent diagram across this terminal 1 and 2. Okay. So this 1 and 2 terminal, we have to make it as a short circuit. And in this short circuit, what is the current flowing? We have to calculate. That is nothing but a short circuit Norton's current source. Okay. So in our diagram, so you see, this is our diagram. In the diagram, this is the terminal 1, terminal 2. So we have to short circuit this terminal 1 and 2. And in this short circuited terminal, what is the current flowing? We have to calculate. Okay. So if we are short circuiting, this means we can get it is a 2-loop circuit. So in this 2-loop circuit, we have to find the current flowing in the second loop. Okay. So in order to find out the current, we may use any procedure. We may use simply KCL or KVL. Okay. So now we are going to use the method. It is a loop analysis, mesh analysis. Okay. So here you just consider it's a 2 meshes. This is the first mesh. So let us consider current flowing in this first mesh is I1. This is the second mesh, current flowing through the second mesh. So already we taken it is a ISC. Okay, so current flowing through the second mesh is a ISC. Our aim is to find out this ISC. Okay, so now in inspection method directly we can write this matrix. So already you know this. This is the R11. What is R11? Total resistance in first loop. So 3, 2. Okay, 2 resistances are available in first loop. So 3 plus 2, 5. Then what is this one? This is the R12. R12 means common resistance between loop 1 and loop 2. Okay, what is the common resistance between loop 1 and loop 2? 2. So the common resistance we have to write it as minus. So minus 2. Similarly, this is R21, R12, R21 values are equal only. This is the R22. R22 means total resistance in second loop. So 4 by 5 plus 2. Okay. So this is the resistance matrix multiplied with, this is the first loop current, this is the second loop current, which is equal to, this is the first, in first loop, what is the total voltage? 2 volt. In second loop, what is the voltage? No voltage, it is 0. Okay. So here, after writing this, we have to find out the determinant of this resistance matrix, and del IC we have to calculate. Then if you are dividing del IC divided by IC, we can get the IC. Okay, so first you just find the determinant of this 2 by 2 matrix. So 5 into 2 plus 4 by 5. So if you are taking LCM, you can get 14 by 5 minus of, you just multiply this two thing. Okay, so minus 4. So the answer for the determinant is 10. Okay, then we have to calculate del IC. What is del IC? In this 2 by 2 matrix, you just replace the second column by this constant value. Okay, so if you are replacing, you can get the matrix 5 minus 2, 2, 0. You just determine the determinant value. So the determinant is 4. Okay, then the ratio of this del IC divided by del. Okay, so del IC divided by del is, call it as the IC value. Okay, ISC value. So determinant del IC divided by del ISC is 4, del value is 10. So 4 by 10, it is a 0.4 amps. Okay, so the short circuit Norton's current is calculated. Then the next one, we have to find out R equivalent. Okay, so in order to find out the R equivalent, this is our given diagram. So in our diagram, we have to find the total resistance across this open circuited terminal. Okay, so in order to find out the total resistance, we have to make all voltage sources and the current sources are 0. So you just make this voltage sources 0. If you are making voltage source 0, this is the short circuit. Okay, so now you see the diagram. The equivalent diagram is, now you see 3 ohm, 2 ohm, 4 by 5 ohm. Okay, so you just reduce from the last end to this end. Okay, so now you see this 3 and 2. What is the combination? This 3 and 2 is in parallel combination. So 3 into 2 divided by 3 plus 2. So the answer is 6 divided by 5. Okay, then that 6 divided by 5 and 4 divided by 5 is in series combination. So 6 by 5 plus 4 by 5. So the answer is 2 ohms. So the R equivalent is 2 ohms. Okay, so we calculated the R equivalent is 2 ohm and the short circuit current is 0.4 amps. Okay, so here you check the answer. So 2 by 5 amps and the R equivalent is 2 ohm. This is the correct thing. Okay, this is the Norton's problem. Then the next question you see, match the list 1 and the list 2. Okay, so here in list 1, resistance R equal to 0, R less than 2 into square root of L by C. In the next thing, R equal to 2 into square root of L by C, R greater than 2 into square root of L by C. Okay, so here undamped oscillation, damped oscillation, critically damped oscillation and a non-oscillator response. So we have to match this one. Okay, so in series RLC circuit, during that is the sinusoidal response. Okay, AC input signal is given in that RLC circuit, means at the time we can get these conditions. Okay, so you just remember this one. Whenever the value of R, okay, the resistance value is 0 in RLC circuit, means that circuit it will produce undamped oscillations. Okay, then whenever the resistance value R is greater than 2 into square root of L by C, okay, this condition is satisfied, means that circuit produce damped oscillations. Similarly, R equal to 2 into square root of L by C. This is the condition for critically damping, okay, critical damped oscillations. Whenever the resistance value R is less than 2 into L by C, that circuit produce non-oscillatory response. Okay, you just remember this using, from this you can get many questions. Okay, R equal to 0 means that circuit produce undamped oscillation. The R value is greater than 2 into L by C means damped. Equal to 2 into L by C means critical damp. Less than means non-oscillatory response. Okay, so this is the thing we have to match. So you see R equal to 0, undamped oscillations. Okay, then R less than 2 into square root of L by C. So less than means it produces non-oscillatory response. R equal to 2 into L by C. This is the critically damped. R greater than 2 into L by C. This is the damped oscillation. Okay, so this is the option. So A is the correct option for the given problem. Okay, you just remember this. The next question, in RLC series circuit, R value given, L value given, capacitor value given, the natural response is dash. Okay, so this question is from the previous this definition, that is if you just check this condition. Okay, R value, L value, C value is given for one series RLC circuit. So if in this 4 condition, which condition is satisfied, that is the corresponding answer. Okay, so you see R is 8, so R equal or not equal to 0, so the first condition is not there. Okay, L is 4 Henry, C equal to 1 by 4 Farad. So we have to check the condition. So we have to find out the value of 2 into square root of L by C. So 2 into square root of what is L? 4 Henry, C 1 by 4. So the answer is 2 into square root of 16, square root of 16, 4. So 4 into 2, 8. Okay, so here the R value is also given as 8. Okay, R value, it is a 8. Then 2 into square root of L by C value, it is also 8. So the condition, which condition is satisfied? This condition is satisfied. R equal to 2 into square root of L by C. So this condition is satisfied means what is the meaning? Critically damping. Okay, so the given circuit, the RLC circuit with the resistance, inductance, capacitance values, this means this is the critically damped condition. The natural response is critically damped. Okay, then the next question, find the voltage VAB of the circuit shown in figure. So this is the circuit. So in the circuit we have to, so you see this is the node A, this is the node B. So we have to find voltage across this node A and node B. Okay, so here some voltage sources are there and some loop is defined with some resistance 3 ohm, 4 ohm, 8 ohm and 2 ohm is given. Okay, so we have to find VAB. So the voltage across, so you see the circuit. So I am redrawing this diagram. Okay, redrawn the diagram like this. So you see the same diagram only. So the here, this is the one loop. So the current flowing through this loop, you just consider as a I. Similarly, this is also a one closed loop. The current flowing through this loop, you just consider as a I2. This is I1. Okay, you just take. So first we have to find out this current I1 and I2. So in order to find out I1, you just write KVL, Kirchhoff's voltage law, to this loop. So if you are writing 7 equal to 3 into I1 plus 4 into I1. So 7 equal to 7 I1. So I1 equal to 1 amps. Okay. Similarly, if you are writing KVL to this loop, okay, the second loop, 10 equal to 8 into I2 plus 2 into I2. So I2 is also 1 amps. So I1 is also 1 amp, I2 is also 1 amps. Okay. Our aim is to find out the voltage across the node A and B. Okay. So voltage across this node A and B. So across this A and B, whatever the thing is connected. So VAB. Okay. So the voltage across this node VAB is calculated as, so 4 into I1. Okay. So the resistance 4 with I1 plus, here you see this is the voltage source. Okay, sorry. This is here, it is connected. Okay, this is the connection. So this is the node A. So if you are writing voltage across, if you want to find voltage across this AB. So you see in A, the resistance 4 is available. The voltage across this resistance, current flowing through this resistance is I1. So the voltage drop across the resistance is 4 into I1. Okay, then here it's a battery, plus 2 minus. So it is also a voltage drop. Then if you are coming here, 8 into the current flowing through this 8 ohm resistor is I2. So 8 into I2. Okay, so you just substitute I1 value and I2 value. I1 is 1 amps. I2 is 1 amps. Okay, just substitute it. So we can get the answer is 17 volt. Okay, so the VAB value is a 17 volt is the answer. Okay, 17. Then the next question, current through the voltage source in the following circuit is dash. Okay, so this is our given diagram. The question is current through voltage source. So here the two sources are given. This is the voltage source, 20 volt battery. This is the current source. So current through this voltage source. Okay, so this voltage source is supplying. You just consider the current supplied by this battery. You take it as a sum IT. Okay, and here there are two branches. In one branch resistance is there. In one branch current source is there. This current source value already given 0.5 amps. Okay, so you just consider current flowing through this resistance is I1. So our aim is to find out this total current IT. Okay, total current IT. So this IT is nothing but it is an addition of, according to KCL, if you are applying KCL to this node, the sum of incoming current is equal to sum of outgoing current. Okay, so that's why the total current is equal to I1 plus this 0.5. So after that, you just calculate I1, then substitute it, you just find the total current. Okay, so first you see, according to KCL, the KCL to node, this node, IT equal to I1 plus 0.5. Okay, so now we are going to calculate I1. So I1 values, across this resistor, what is the voltage given? 20 volt. So voltage across this resistor is 20 volt. So current flowing through this resistor is this 20 divided by the resistance according to Ohm's law. Okay, so the current I1 equal to 20 divided by 10, 2 amps. Okay, so substitute this I1 value in above equation. So the total current is equal to 2 plus 0.5. It's a 2.5 amps. Okay, so the answer B is the correct answer. Okay, so this is the one type of question. And the next question you see, a DC voltage V is applied at a time t equal to 0 across RC circuit. Okay, the steady state current is dash. So across one RC circuit, one series RC circuit, the voltage is given. What is the steady state current? Okay, so already you know the formula, the current flowing through this series RC circuit already I given in the previous thing. Okay, in that if the current flowing, so this is the graph for the corresponding current flowing in the RC circuit. So initially the current flowing through this series RC circuit is maximum V by R. Okay, then slowly it decreases with respect to the time constant tau. Okay, so at a steady state or time t equal to infinity, the current flowing through the circuit reaches 0 value. Okay, so the capacitor is open circuit for the DC supply. So the current flowing through the circuit is 0. Okay, so steady state current is 0 for this RC circuit at time t equal to infinity. Okay, so these are some of the questions. So we will discuss the remaining questions in the next video. So thanks for watching my channel and please subscribe my channel for more videos. Okay, so already I posted some of the videos related to the TRB exam. Okay, if you want to learn that one, I will give link in the description box. You can use it. Okay, thank you. We will meet in the next video.